So this is the last lecture on, on the magnetic properties of materials. And so we're continuing our investigation into superconductivity, and we are going to look at the concept of a critical current in this first part of the lecture. Now, I just want to return to the very last bits of the last lecture in which we were looking at the penetration depth, so how far the magnetic field will penetrate into the superconductor. There's just one thing I forgot to mention. So we came up with this with an expression here for the London penetration depth. Okay, and that depends on a bunch of constants, m, mu naught, and q that we can't change. But what about n? So n is the superconducting density. What would happen as we approach the transition temperature from below? Okay, well, n is going to decrease. As we reach Tc itself, n will go to 0. So what that means is that this this depth is going to get longer. Okay, so we're going to expect something like this to get longer and longer. So as we approach Tc, the magnetic field can penetrate deeper and deeper into the material, and at Tc itself, n will go to 0, and hence the penetration depth is infinite. So the material has now become normal, and the magnetic field has been able to penetrate completely through the material. Okay, so I just thought we'd look at that as a consequence. So I just want to think about resistivity for a little bit. So just first of all, resistivity in normal metals, and we can look at two different contributions. So elastic effects, so that's where the energy doesn't change, but there's just a change in direction of the electron. If you like, it's just the electron's momentum is changing. So that would be, for example, scattering from defects. Okay, there's no energy loss. The incoming particle just changes its direction afterwards. But we can also have inelastic collisions. Okay, so the electrons can interact with phonons, lattice vibrations, and in that case we would expect a change in energy and a change in momentum. Okay, the phonons will take away both energy and momentum from the electrons. Okay, so these are the two loss mechanisms we have in normal metals that leads us to resistivity. So we need to look at why do these mechanisms not affect a superconducting current. Okay, well, let's just remind ourselves that in the ground state, the superconducting ground state, we've got essentially a coherent wave function. Okay, we can write it like this. All of the Cooper pairs have the same wave function. Okay, this is coherent. Now, it's worth making the point that many Cooper pairs occupy the same volume. We saw earlier, back of the envelope calculation gave us the separation of the Cooper pairs to be, 2,000 angstroms. That's pretty big. There's going to be a very large number of Cooper pairs in that same volume. In fact, there will be millions of them. Okay, and there will be a sense of dynamic equilibrium between the normal electrons and the Cooper pairs. What do I mean by dynamic equilibrium? Equilibrium because the number of each remains constant. Dynamic because the situation is changing in the sense that we will have two electrons that will come together and become Cooper pairs, and Cooper pairs that will split themselves apart and convert into two normal electrons. So the total number is the same, but if we were to look at a sort of microscopic picture, we would see there's a lot of activity going on. Okay, so let's think about in the conducting state. So we've got a coherent wave function, but now the wave function has an overall momentum. Okay, in this the way I've written it out here, the momentum would be P would be equal to h bar capital K. Okay, so all Cooper pairs have exactly the same momentum. Okay. Now we can have elastic collisions, so that's a change in defect. So a Cooper pair could come along and it could bump into a defect and it could try to change its momentum. Well, it can't, because all Cooper pairs have to have the same wave function. They have to have the same momentum. So if our Cooper pair had a different momentum, it wouldn't be part of the coherent ground state, and in fact it would therefore lose its energy. Okay, so we would need to have a change in energy, and that's not an elastic process. So the only way we can change the momentum of a Cooper pair is if we change the momentum of all the Cooper pairs in the whole material. So we change the direction of the current that was flowing. Okay, so scattering off a defect, that's forbidden. That can't cause any change in the momentum. So there's no resistivity from elastic scattering. What about inelastic scattering? Well, we need to change both the energy and the momentum. So I'll give you two versions of this. The simple version is just to say, well, that's forbidden because we would need to supply, a normal electron in a normal material can change its energy infinitesimally. In the condensate, in this superconducting state, they can only change for a Cooper pair to change its energy, it would have to increase by 2 delta. Okay, it can't increase by like half a delta, it has to be 2 delta that it increases its energy by. So that means that scattering from phonons, so inelastic scattering, is forbidden. Let me give you another version of that, okay, because what I told you before about this dynamic equilibrium where electrons and Cooper pairs are being continually interconnected, that is in a sense a type of inelastic scattering, and so we should consider that a little bit more carefully. So what have I got? I've got really, I can draw this sort of picture where I've got a Cooper pair that comes in. So this is my Cooper pair, and it's going to interact with a phonon, and that will give me 2 electrons. Okay, so that's a process that happens, but I know that that process there must be an equal and opposite process, because I can have 2 electrons that come together, giving me a phonon and giving me my Cooper pair. Okay, now so this process is going on all the time, but the thing is that does this lead to any resistivity? Well, it would do if the Cooper pair, the incoming Cooper pair and the outgoing Cooper pair had different momenta or different energies. But from the argument that we had before, they can't be, because this Cooper pair has to have the same wave function as all the other Cooper pairs, otherwise it's not bound. So the only process in this dynamic equilibrium that can go on is one Cooper pair comes in with a particular momentum, and the Cooper pair comes back out again with exactly the same momentum. So interacting with phonons in this way, this type of inelastic scattering, doesn't lead to any resistivity. So if you like, it's the fact that we have this coherent wave function, this everything in the same state, that protects the current. But, okay, you might imagine though, the more current we put through, that means the greater the momentum, okay, because the Cooper pairs are going faster, so K is bigger. And there must become a point at which the excess energy that they have over, say, a normal electron is sufficiently great that it will be greater than, say, the binding energy of the Cooper pairs. So I can make these Cooper pairs go faster and faster and faster through the material, and at some point they'll have so much extra kinetic energy that will be greater than their binding energy, and so at that point they can split apart. They can take the energy from their momentum and use that to split themselves apart. And so what that means is that all superconductors will have a critical current. So there'll be a limit on how much current can actually pass. So let's have a go at see if we can estimate that, because this is going to be it's a really sort of critical property in terms of the use of superconductors. Okay. Right, so I'm going to write this out, and but it does appear neatly in the following 2 slides. Okay. So let's consider a Cooper pair with momentum P equals h bar, and I'll draw my capital K's in blue. Okay. So we can write the momentum of the two electrons as, I can write them like this, K1, K2. Okay. And well, what must that be equal to? Well, we know that in the ground state, K1 equals minus K2. Okay. So this would be K. Now we need to, this overall state has momentum K, capital K. So both of the electrons gain half of that. Minus K plus that'll be a half capital K. Okay. Now, what else do we know? We know that K is about Kf. Okay, it's about the energy at the wave vector at the Fermi energy. Okay, so let's consider the first electron. So for the first electron, the difference in energy call it delta E, and this is from the superconducting state to the normal state. That will be given by, so delta E will be equal to h bar squared over 2m. Remember the formula for kinetic energy is h bar squared k squared over 2m. And so that's going to be the energy of the first one, which would be kf plus capital K over 2 all squared minus the energy now in the normal state, which is just kf squared. Okay, so we can expand that, and when we expand the brackets, the k squareds will cancel, and I'm only going to keep the term that's linear in the blue k, because k is quite small. Okay, so that would give me h bar squared over 2m kf times k. If you like, it's plus order blue k squared. Okay, which I can neglect. So that's my term for the change in energy. Right. So let's consider the current from this. Okay, so if we look at the current coming from the first electron, we have that J is equal to minus density EV, charge times velocity, where mv, the velocity, is going to be h bar over 2 times k, blue k. Okay, remember, because that was the momentum of the Cooper pair. Okay. So this tells me that, subbing in for v, this tells me that J is equal to minus ns e h bar over 2m times blue k. And using the formula from previous, that will subbing that in, that will give me that delta E is equal to h bar kfj over e ns. Okay, so just perhaps pause the video for a second, just look back at the previous slide and convince yourself that this is the case. So this tells me that there's that the energy difference is related to the amount of current that flows. Okay, so the higher the current, the higher the energy difference between the superconducting state and the normal state. And there must be a critical current, so there is a critical current. And we'll call it JC, such that two times delta E is greater than or equal to the binding energy. Okay. So if we look for equality, that would tell us that Jc equals E to the ns delta over h bar kf. Okay. So there exists a critical current in the material that's a property of the intrinsic things such as the superconducting density, the Fermi energy, and also the gap. So the superconducting current is closely related to the gap. That's important because as we know, the gap varies with temperature. So if the closer we are to the transition temperature, the smaller the gap is, and hence the smaller the critical current is. So if we want a material and we want to use it for carrying large currents, like for example in a superconducting magnet, we don't just want to take our superconductor down to Tc, we'd like to take it well below Tc, because then the critical current it can sustain will be much greater. Okay. Just as an example, so for tin, at low temperatures, we have that Jc is the order of 2 times 10 to the 11 amps per meter squared, just to give you an indication of that. Now, of course, the fact that we've shown that there's a critical current also means there's a critical field. So that was one of the very early things that we did in 3 lectures ago. We talked about that there was a critical field beyond which we destroy the superconductivity. Why is that the case? Well, if there's a critical field, we know that, if when we've applied a magnetic field, we know that there'll be superconducting currents that flow around the outside of the material to remove the magnetization inside the material. And what's important is not the origin of those currents. It doesn't matter whether we are actually physically passing a current through the wire or whether we've put it in a magnetic field and there are currents flowing. It's the total current that flows. So there will always be a critical field that causes a critical current to flow in the material. Okay, and so if I go higher than the critical field, the current will be higher than the critical current. That'll be enough energy to destroy the Cooper pairs, and we go back into the normal state. Okay. The other implication of this is that let's imagine I've got a particular critical current at 0 field. How does the critical current change as I apply an external field? Well, the amount of current I can pass before driving the material normal is now lower, because there is already a current that's coming from the screening. So there's the screening current, and it's the sum of that screening current plus the actual current that I'm passing through the material. And it's when that sum is equal to Jc that we drive the material normal. Okay. So, okay, these are the same slides written out just a little bit more neatly. So I want to return to something again from about the first lecture, and we looked at a variety of values of Tc and the critical field for elementals, metals. And we saw that mostly the critical fields were really quite small in terms of Tesla. I should say these units are obviously here. That this is Kelvin and this is Tesla. For something like lead, the critical field is actually tiny. It's 0.08 Tesla. So for most elemental metals, the amount of field that it can sustain, and hence the amount of current it can sustain, is really very low. So elemental metals are typically not very good for any current carrying application. Okay, you wouldn't make a particularly good. You could only make a very weak magnet out of some lead superconducting wires. But I remember that in that list I had vanadium, and I probably should have put niobium as well. And the thing about vanadium and niobium is the Tc isn't very much different, but Bc is a lot larger. Okay, and I said we'd return and we try and understand that. Now, if you come to alloy metals, so here I've got niobium and titanium. So I add some titanium in. What happens? Well, interestingly, the transition temperature doesn't really change. Okay, titanium doesn't have a very high superconducting superconducting transition temperature to about less than a Kelvin. So there's very little difference on the transition temperature, but look how much the critical field changes. Okay, a huge amount. 15 Tesla is a very large magnetic field. So there's something very different in this material. It can stay in a much larger critical current or a critical field. Some of the highest fields we have are something like niobium and tin, both good superconducting elements. When we alloy them together, we get reasonably high TC, and the critical field is now 30 Tesla. So this is starting to be sort of technologically useful for producing magnetic fields in for NMR or for MRI machines. And it turns out that there is a critical difference between these elemental metals and, well, just a small number of the elements, niobium and vanadium, but typically the alloyed materials, which have a very different magnetic behavior. Okay, and what I've shown down here is how we expect a typical superconductor, elemental superconductor to behave. So as I increase the field, okay, across here, what we know is that there will be screening currents which will perfectly cancel out the magnetic field. So the magnetization is the exact opposite of the applied field, so that inside there's no magnetic field. This is the perfect Meissner effect, perfect diamagnet. And that happens all the way up to a critical field, at which point the material goes back to normal. So here we're superconducting and here we're normal. And so these type 1 materials typically cannot support very large magnetic fields. What it was found was that these, when we alloy the materials, we get a different type of behavior. So initially it starts off the same. Okay, as we increase the magnetic field this way, then we get the perfect diamagnetism. But now at a slightly lower field, this changes, and the magnetization is less than what it would be needed to cancel out the applied field, and the magnetization response is less than what we need to cancel it out. What that means is the magnetic field is now able to enter the superconductor. So up to this point, we've got perfect diamagnetism, and beyond this point, the magnetic field has in some way penetrated into the material. The material is still a superconductor because it's still able to pass a current without resistance, but it's not a perfect diamagnet. And the type 2 behavior means that it's able to actually go to much larger fields. So the superconductivity vanishes at this point down here, not this point here. Okay, so type 2 materials can actually have much larger critical fields. And this means they're much more useful in technological applications. Now, we need to try and understand what the difference is between a type 1 and a type 2 superconductor from the theory that we have. And actually, there are two different length scales that are important in superconductivity, which come out from BCS. They also come out from this Landau-Ginzburg model. And one of them we've met already, and that's the London penetration depth. Okay, that's lambda given here. And this tells us about how far the magnetic field penetrates into a superconducting material. There's another parameter, which is the coherence length. And this is given by, again, a series of material parameters. And it measures the uniformity of the superconducting wave function. So if the coherence, so if eta is large, that will favor a wave function that is uniform on a long distance, okay? And if eta is small, this will mean that the wave function is able to modulate itself in some way, okay? So, I mean, modulations in a wave function are typically increased kinetic energy. Okay, so being able to calculate from the material properties these two parameters allows us to estimate whether a material will be type 1 or type 2. Um, let me just look at this. Okay, I haven't written this. I haven't put a blank slide in, so I'm just going to talk through this rather than writing it out. So what we need to think about is at the boundary. Okay, and I've got different energy terms. Okay, so we know that at the boundary. So let's imagine I've got a boundary between a normal material and a superconductor. Okay. Well, first of all, we know that the if we look at, for example, the B field, okay, that would do something like this. It would penetrate into the material. So this is a 0. Okay, and this region here, this is lambda. Okay. So by doing that, the larger lambda is, so we get a decrease in the free energy. Okay. So this is, we calculated this factor before. So the larger that lambda is, the larger the decrease in the free energy. Okay. But if we look at, for example, let's look at the gap in the material. Okay, so if we're going to look at the gap. So the gap will be uniform, and then it will decay to 0. Okay, so this is what the gap will do. Okay, so this region here is the region in which the superconducting wave function is changing. Okay, and the larger that eta is, the larger this region can be. Okay, so let's put on this is eta here. Okay, and the larger the eta is, actually the higher the energy in the boundary, because we've got a region. So this is the region where everything is coherent and all in the same superconducting state. This is a region that isn't all in the same superconducting state, so this is a higher energy region. Okay. So I've got this tension between these two energies, and so the boundary energy will be the sum of these two things. Now, interestingly, we found very early on when we did the thermodynamics that the factors at the front are roughly equal to each other. So whether the surface energy is positive or negative just depends on the ratio of these two parameters. So if eta is greater than lambda, the boundary energy is positive. Okay, so having an interface costs energy. And so the material wants to have as fewer interfaces as possible. So it only has an interface at the surface. Okay, so it has to have one at the surface. So that's the only interface that it has. But if we're in the other regime, the surface energy is negative. So it can be favorable for the material to have multiple surfaces. And this is indicative of the type 2 behavior, because we're expecting to have when we're in the higher field state, we end up with positions where we're going to have an alternating superconducting normal. Okay, and that's how the magnetic field is going to penetrate the material. So I've drawn this out just schematically, showing you here how the B field varies and is determined by the penetration depth lambda, and how the gap varies with the coherence length. Okay, and we've got the situation of type 1 and the situation of type 2 where they're reversed around. Okay, so just to summarize, we've got our type 1 material in which interfaces cost energy, and so that we only have our interface at the surface of the material. And there we get the perfect diamagnetism all the way up until the critical field. And then our type 2 material, we get perfect diamagnetism up to this first transition energy here. I've called this BC1. And between these two regions, we get penetration of the field. And so what that means is that inside the material, we have alternating regions of superconducting and normal. Okay, so the magnetic field is penetrated, but there's still superconducting pathways, so this still has dissipationless current. And it's actually quite interesting. You can look at these with an electron microscope and see what pattern is how this actually does it. I mean, we can imagine lots of cases. We could have stripy materials, all sorts of things, but it actually does it like this. So let's take a cross section where the magnetic field is, say, coming out of the page towards us. And what happens is we get little regions like this. Okay, and they're arranged in a kind of triangular lattice. Something like this. Okay, and so in these little regions, so this is normal. And the rest of the material is superconducting. Okay, and these are actually little vortexes, because what these will be is there will be little superconducting currents that are going round here, allowing a magnetic field in this region here, but screening it from the region outside here. Okay, and as we increase the magnetic field, we get an increase in density of these little vortexes. Okay, but there'll be more about that in this has implications for practical superconducting materials and devices, and so there'll be more on that in the third year option course. So I just wanted to finish with a summary. This is the same summary slide we had in the first superconductivity lecture, and let's just check that we can understand things. So we now know that there's so we know experimentally zero resistivity below a critical temperature. Okay, we now know that's because of the formation of Cooper pairs, where there's this attractive force between electrons mediated by their lattice. We also know that superconductivity vanishes above a critical magnetic field, and we've been able to understand that in terms of a critical density, a critical current density that flows in the material, whereby there can be enough momentum to give enough energy to break apart the Cooper pairs. We noticed there was an isotope effect, and we can understand that because we found that our superconducting transition temperature was related to the Debye frequency, and the Debye frequency was related to mass. So we understand the isotope effect. We knew experimentally the Meissner effect, that the material expels the magnetic field when cooled below the transition temperature, and we understood that in terms of this rigidity of the wave function, which led to the London equations, which predicts the Meissner effect. We've also found that it can be more complicated in, for example, type 2 materials, where we get a phase in which the magnetic field can penetrate and it's not a perfect diamagnet. We knew experimentally that there was a jump in the heat capacity at the transition temperature. We always expect jumps in heat capacity to be related to an excitation effect, and indeed here the excitation effect is the breaking apart of Cooper pairs. Okay, that if we give enough energy, we can break apart a Cooper pair. And finally, we discovered that we knew experimentally that, for example, optical absorption, so in the light regime, was the same between a superconductor and a metal. But in the microwave regime, there could be a sort of transition threshold in which we'd go from absorption to no absorption. And we understand that in terms of a gap, where the gap is in the millikelvin regime. So that's directly in the microwave region. Okay, so I hope in the previous lectures I've been able to convince you that that BCS theory actually accounts for the magnetic and thermodynamic properties of superconducting materials, at least those that are comprised of elemental metals.